Hello everyone, and welcome back for another round of Circuit Golf. In today's Circuit Golf episode, we are going to build a MOSFET-based solid-state relay, and the reason is that I happen to need one of these for a project I was working on for a friend. Let's just dive right into it. The heart of this thing is actually these two MOSFETs right here. Now, I've selected a couple of MOSFETs that are 650 volts N-channel MOSFETs with a 340 milliohm R-on. These aren't actually the MOSFETs that I would actually use if I was going to build this. They were just the closest thing I could find in LT-Spice. The theory behind how this thing works is basically the reverse body diodes on these MOSFETs. When the MOSFETs are turned off, those diodes essentially sit back to back. They block any attempt by this AC source right here to send current either way through the MOSFETs. If it tries to send current through this way, this diode blocks it. And if it tries to send current through this way, then the body diode here blocks it. So you have a relatively good setup to prevent the AC from flowing when you don't want it to flow. Now, what about when you do want it to flow? Well, then you turn on the MOSFETs by pulling their gates high, and the channel of a MOSFET transistor conducts electricity in both directions. So when this AC source is positive on this terminal, it flows in through this MOSFET along this wire and back out through this one. Or, it could detour through the body diode here, but since the MOSFET channel is open, most of the electricity will choose to go through that instead of going through the body diode. Likewise, if the top terminal of this AC source is negative, that means this is positive, and the electricity, the conventional current, will flow through this channel across this wire back into the voltage source through the channel, or maybe some through the body diode of this MOSFET here. So that's a relatively simple explanation of the heart of it, but there's some less than obvious problems with it. The first problem is that because there's only going to be a small on resistance from these MOSFETs, this wire down here might float up and down in voltage quite a lot, particularly, depending on how you hook up the load and the voltage source to it. What you end up having to do is two things. One is the control signal has to come through an optocoupler, and the control signal just basically allows current to come in through Q1 here. The current charges up the gates of the MOSFETs and also causes a voltage rise because of the resistance of this resistor. The ground node here is floating. It floats right along with whatever voltage is on this wire. And that leads us to the second sort of non-obvious consequence, which is the voltage used to charge up these gates has to float along with this bottom wire down here. So you need to use a transformer in order to get that floating voltage that will float along with whatever it is that you're hooking up as the load and the voltage source. I think it's worth saying that in LT-Spice, there are no transformers. These are merely two coupled coils, and what looks like the core of the transformer here are simply two wires that I put in that look like a ferrite core, but they are not. They are simply two pieces of wire that I put in there to look cool. If you hit F2 in LT-Spice to try and find a transformer symbol, you're not going to find it here. You can dig through the menus all you want. There is a good page on the LT-Spice wiki talking about how to make transformers using coupled coils, and I will put a link to that down in the video description. But just so you know, there is no pre-made symbol for a transformer in LT-Spice. Instead, you have to do a Spice directive K for coupling L1 and L2 to couple these inductors. Beyond that, it's fairly conventional. On the secondary side of this transformer, you have a standard diode bridge here that just, full wave rectifies. Thank you, Medi. Then it goes into... I'm not in any way wedded to this LT1962 voltage regulator. I just picked this because it was the easiest, simplest, and most convenient micropower low dropout voltage regulator. You could put a straight 7805 in here for all I care, or 7809 in my case, and it wouldn't bother me one bit. So just know that I'm not recommending this particular part. I'm just using it as an easy adjustable voltage regulator That's about it. So yeah, basically what you get out of this is you get a floating 9-volt voltage that is regulated pretty well and is relative to this ground here. And that ground here floats up and down with whatever voltage is on this wire, which is caused by whatever load you have. And again, I'll say this again, you heard me say it earlier, but the control signal also has to be isolated because it also could be at a very different potential than what the source pin of these MOSFETs, or the source terminal of these MOSFETs, is actually seeing. So you have to optocouple that. Those are the two tricks that actually make this work. You know, you've got a good idea here, but the life support to make the whole thing work is a little more complicated than it at first appears. You have to essentially float your control signal and float your power supply through a transformer. So let's take a look at this in action. And this actually brings me to the last thing I wanted to let you guys know, which is if we just put this circuit into SPICE and press the go button, watch what happens. Oh no! SPICE can't analyze the circuit. For some reason, the conventional solver, when the gates of the MOSFETs turn on, maybe it's this floating thing, I'm not sure, it simply cannot handle. If we look at VGate, you can see over here, VGate starts to go high, gets to about 3.8 volts, and then the solver just blows up and LT-SPICE can't analyze the circuit. So to fix this, we have to go to Tools, Control Panel, the SPICE tab, and set this to the alternate solver. And you can see down here in the lower right, it now says alternate. And this is a setting that most versions of LT-SPICE will remember across runs of the program. So be sure you turn it back off back to the conventional solver before you exit the program, or you'll be on the alternate solver next time. So let's go ahead and delete this. And we will run it again. Okay, so it ran successfully. Let's start probing a few nodes just for giggles. Here's the unregulated voltage coming out of the diode bridge. You can see it stays well above 12 volts, starting at about 30 milliseconds. And here is our nice, clean, regulated 9 volts. Lastly, let's take a look at the on-off signal, which is the one that's being optocoupled through here. You can see that the on-off signal comes on right around 100 milliseconds and flips off right around 200 milliseconds. So the solid-state relay is on for about 100 milliseconds, between 100 and 200 milliseconds, and it's off the rest of the time. Let's get rid of this VREG. Well, let's just get rid of all of these. And let's look at a couple other things. So first of all, let's look at the control signal. Well, let's look at the control signal. Actually, let's look at V-gates, the gate signal, the voltage on the actual gates of the MOSFET in green. And then let's look at the control signal in blue. So you can see that basically this on-off signal either turns on or off the base of this PNP transistor, which then lets the current flow through to charge up the MOSFET gates and also create that voltage drop across R1. And then for our other thing that we want to see is it actually working? Let's take a look at the current going through R5, this 120 ohm resistor. This is a 120 volt RMS AC source right here. Not the same as this one. First of all, it's a 50 hertz, whereas this is a 60 hertz. I did that intentionally to see if there would be any kind of weirdness when your input and your power supply went out of phase with each other. As far as I can tell, there is none. Anyway, let's look at the current going through this resistor that's connected to our AC source when the relay is on versus when it's off. So as you can see over here on the right, when your V on, V off is off, unfortunately this is reverse polarity, but basically you can see the correspondence between V on, V off being active and inactive. So this does actually switch that AC source on and off. Basically, it all just works. That is Circuit Golf for today. I hope you've enjoyed that. I will also put a link to the .asc file in the description, so if you want to download this and play with it, be my guest. I thought this was a fun little project, and maybe someday I'll actually get to tell you about the larger device that this is integrated into. But for the moment, I just thought this was a neat little exercise, and I wanted to share it with you. And by the way, I want to disclaim, this is absolutely not my original idea. I read about this in a datasheet or an app note somewhere, And that app note was probably published 15 years ago, maybe even 20 years ago. I didn't come up with this. This is just my particular implementation of the idea. Someone much smarter than me had this idea first, and I just wrote up a little circuit diagram to actually implement it. All right, I hope that was fun, and I'll see you next time.